Welcome to The Explainer. Today we are diving deep into this invisible science, electrochemistry, and you're going to see how it shapes our world in two wildly different ways.
Okay, so on one hand, it's this silent, controlled flow of energy, right? It's what brings all our essential modern tech to life. I'm talking about the phone in your pocket, the laptop on your desk, even the car in your driveway.
But, and this is the crazy part, that exact same force, when we just let it run wild, is also responsible for the slow, relentless decay of our world. Think about the rust on a bridge or the corrosion on a pipe. So what's the deal here? How do we even begin to understand this powerful duality? I mean, a science that both creates and destroys. How can one single principle be behind both incredible progress and total decay? Well, the answer is a field called electrochemistry. And really, at its core, it's all about controlling the flow of these tiny little particles called electrons. See, when we get that flow under control, we can turn chemical energy into the electricity that powers, well, everything. But when we lose control of it, that's when you get all that destructive damage. All right, so let's kick things off with the side of electrochemistry that we all know and love, even if we don't think about it. We're talking about harnessing that electron flow inside the batteries that literally power our world. Okay, so when it comes to batteries, you can pretty much split them into two main groups. First up, you've got your primary batteries. The easiest way to think about these is like a one-way street. The chemical reaction happens, it gives you power, and then that's it, it's done. But then you have these secondary batteries, and these are the rechargeable ones we use all the time. Their chemical reactions are totally reversible, so it's more like a two-way street. You can go back and forth. And if you look here, you can actually see the specific chemical recipes that make all that power happen. It's pretty cool, right? Just notice how the materials change depending on what the battery is for. A simple TV remote, it gets a basic zinc and graphite setup. Your car battery, though, needs that heavy-duty punch from lead and lead oxide. And of course, for the really high-performance stuff like laptops and EVs, we're all about that lightweight, super-efficient lithium-ion tech. So you see, every combination is specifically tailored for its job, but the fundamental idea, that controlled flow of electrons, is exactly the same. But what happens when that flow of electrons isn't stuck inside a nice, neat little battery case? Well, now we're going to flip the coin and look at the other side, that uncontrolled, totally destructive process we all know as corrosion. So what is rust, really? I mean, what's actually happening? You might be surprised to hear that it's basically the result of millions of tiny, natural electrochemical cells just popping up all over a metal surface. It's almost like a battery working in reverse, but instead of giving you power, it's just draining the life and structure right out of the metal. And believe it or not, this whole thing can kick off in just a single droplet of water. So, you get a spot with low oxygen, and the iron there becomes what we call an anode. It starts to dissolve and lets go of its electrons. Those electrons then zoom through the metal to an area with more oxygen, the cathode, and that's where they react. And for the grand finale, those dissolved iron ions mix with water and bam! You get that flaky, reddish-brown stuff we all recognize as rust. Okay, so if corrosion is basically just an unwanted natural battery running amok, then it stands to reason that the key to everything is figuring out how to understand it, how to prevent it, and ultimately how to control that unwanted electrical current. And the good news is, we've come up with a whole toolkit of really clever ways to fight back. You know, we can do something simple like just putting up a barrier with paint. Or we can get a bit more sophisticated and use something called cathodic protection. This is where you attach a sacrificial piece of metal that basically takes one for the team and corrodes instead of the important structure. We can even change the metal's basic properties by mixing it with other metals to create alloys, like stainless steel, which is just naturally good at resisting rust. But here's the thing. In science, you can't really control something until you can measure it precisely. And for electrochemistry, the big measurement is conductivity. We need to know exactly how well a solution can carry an electrical current. So how do they do that? Well, it's a pretty ingenious process. First, scientists have to use an alternating current, or AC. Why? Because if they used a direct current, the kind from a regular battery, the very act of measuring would actually change the chemical solution they're trying to study. So they pass this AC current through a special circuit called a Wheatstone bridge, which lets them balance the electrical flows with incredible precision. Once they find that perfect balance point, they can calculate the solution's resistance, and from there, its conductivity. And that is the critical piece of data you need to really get a handle on these reactions. And maybe the absolute pinnacle of controlling these reactions is the fuel cell. I mean, this thing represents a cleaner, more direct, and just ridiculously efficient way to generate electricity by harnessing a perfectly controlled chemical reaction. Now, unlike a regular battery that holds a limited amount of energy, a fuel cell just keeps on running as long as you keep feeding it fuel. Take a hydrogen-oxygen cell, for example. You've got hydrogen and oxygen gases flowing past these special porous electrodes. They react, create an electric current, and guess what the only byproduct is? Pure water. That's it. It is an unbelievably clean and efficient way to make power. So, at the end of the day, whether we're talking about powering the phone in your pocket, stopping a bridge from crumbling into the river, or designing the clean fuel cells of the future, it all comes down to this: mastering that invisible flow of electrons. The whole story of electrochemistry is really about our ongoing quest to control a fundamental force of nature. And that, well, that just leaves us with one final thought to chew on. Just how perfect can we make that control?